In this tutorial we'll look at a CLS specimen, which is displayed here. The crack lab shear specimen is used to investigate different mixed mode ratios in fracture mechanics, and therefore is a field of study at the University of Stuttgart at the Institute of Aircraft Design. As you can see here, the crack lab shear specimen is divided into two parts. The lower part, which is in a length greater than the upper part. The lower part is introduced with a force or a enforced displacement on the right side, which induce a bending moment at the bonded nodes displayed in red. We model this crack lab shear specimen with conventional shell elements as 4 in Abaqus 6.13. Let's first create the parts. The first part, the lower part, is 150 millimeters long, and the width is 20 millimeters. Okay, create part. Part 1, 3-dimensional, deformable, shell, planar. Okay, we use the rectangular shape to define the shape of the lower part, which is 0, -10 and 150, 10, which is a rectangular shape. We can click OK to that. And it's named part 1. That's maybe not the best name. We can rename it to lower part. And do the same thing for the upper part. 3-dimensional, deformable, shell, planar. Continue. And here we can see that the upper part is 90 millimeters in length and also 20 millimeters in width. So this time the parameters are 0, -10 and 90, 10, which is again a rectangular shape. Now, as we have to define a contact later on, we have to define master and slave surfaces, and it is advisable to define them in the part module in Abaqus. So we can say tools surface create, and now I'm on the upper part, so this will be the slave surface. I can select it and click done. The upper part has its internal faces on the lower side, so it's purple in this case. And the lower part, tools surface create, is the master surface and has its internals on the upper side, so it's brown in this case. Okay, now that the surfaces are implemented, we are done with the part module, and we can proceed to the property module. In the property module, at first we have to define a material, which in this case will be a carbon fiber reinforced plastics with isotropic material modeling. Mechanical elasticity elastic with a Young's module of 62,600 newtons per square millimeters and a Poisson ratio of 0.3. We can now define a section. The section will be a shell section, homogeneous, and will be used for both parts. It has a thickness of 2 millimeters and the material we just created. All other parameters are sticked with the default. Now when it comes to section assignment, we have to define the shell offset. So we just click on shell assignment, select the part. We don't need a set for that. And now we're on the lower part. The lower part is modeled like this, and it's therefore the upper surface which is modeled. So we have to select in the definition the upper surface, top surface. Same is valid for the upper part, which in this case will have the bottom surface, as you can see here. Upper part, bottom surface. Now we can move on to the assembly. The assembly, as we defined the parts in the same coordinate system in the same way, we don't have to think about offsets, and we can just include them in the assembly. We can now also create datum points via tool datum, enter coordinates. The first one is located at 75 millimeters and the second one at 150 millimeters. The first one defines the crack tip, which we can see here with 75 millimeters, and the second one is used for load introduction on the right side for a coupling. We create a step, static general, which has a time period of 1 second. The nonlinear geometry has to be enabled. We do not need automatic stabilization, as we don't see debonding in this case. We have the incrementation, and we can stick with the default for this case because we don't have debonding happening. If we would have debonding happening, we would have to decrease this value for the minimum time increment to 1 to the power of minus 15, something like that. Okay, also we can define the field output, and for that we have to enable fracture failure outputs because we are interested in the bond state, the energy release rates, and the effective energy release rate ratio. Also interesting maybe is the time at bond failure and the opening behind the crack tip. Now let's move on to the interaction. The interaction module is the module where you can define the contact definition. And in this case, we want to define an interaction as a surface-to-surface contact. And now the surfaces come into play, which we defined earlier in the part module. So we click here on surfaces. We have to select the master surface first. So we click on the master surface and then on continue. The slave type is surface in this case. And we select the slave surface equally to the master surface. Now the contact definition is established with small sliding theory, node to surface discretization, and the default parameters for the different values here. What we have to do is to assign a clearance, and it will be uniform across the surface, and it will be 1 to the power of minus 8. Click OK would get me an error message because I didn't define the contact interaction property, which I have to do. And I'll do that with the click of the button here. It's a contact property, and we have to assign two things. The first one is a fracture criterion with the default parameters VCCT, maximum tangential stress, PK model, 0.2 tolerance, viscosity. If this would have been a debonding scenario, I would have enabled this, the tolerance for unstable crack propagation, and it helps the model to convergence. The convergence is better with the unstable crack propagation. What we have to do in both cases is to implement the critical values for the energy release rates, which is in this case 0.6 for mode 1, 7 for mode 2 and mode 3, and 1 for the beta, for the eta exponent used for calculating the decay model. The second thing we have to add is the geometric properties. And as we have a out-of-plane surface thickness, we have to define 2 millimeters here. Okay, now the contact property is set, and now I should get no error message when I click OK to the contact definition. Contact is established. The next thing we have to do is to include a set in the contact definition. That's the thing I forgot. As you can see in the contact definition, we have a bonding here, and it says limit bonding to slave nodes in the subset XX, and XX is the one we have to define now. So we go to mesh and mesh both parts with equally distributed 1 millimeter meshes. 1 millimeter for the upper and lower part, which results in matched meshes, as you can see. And now we can define our bonded nodes, set create, node set, and let's call it bonded nodes. And you see the datum point here we created earlier at 75 millimeters. That comes now into play. So let's take all the nodes except the last row, because the last row is defined with boundary conditions, and boundary conditions and the bonded nodes, they don't like each other. Okay, now the contact property is set. Next thing to do is the coupling on the right side, and therefore we need a reference point. A reference point goes to the datum point we created earlier, and the coupling is defined with a coupling, which we select in the viewport. Master is the reference point, done. Constraint region type is node region in this case, and it's the edge here. Done. It's a continuum distributing coupling, and we don't need the rotational degrees of freedom as we just introduce a translational force. Okay. Now that the constraint is set, we can go to the boundary conditions in the next module. In this module we have the left side, which we have to constrain, and the right side as well. Let's discuss that at the drawing. The left side is completely fixed, so there's no way that it can move. The right side is also completely fixed, but it can move in the X direction. So for the boundary condition, this means I can apply a displacement rotation boundary condition named fixed to the left side of the specimen. And now here's really important that you select both edges. You have to do this with the selector set to edges and go with the rectangular shape over both edges. Because, you know, there are two parts here and the edges lie on top on each other, and if you just click on here, you may select only one edge. And that would not be the case, not be right. Okay, now we can say everything shall be 0 except the translational degree of freedom in the y direction, because we want to constrain this direction just with a point load, with a point constraint. Let's add the point constraint as well. Same valid for this constraint. Select the selector to add to vertices, and go with the selector over the points at the end of the specimen to catch all 4 points. Select the y direction translational degree of freedom to 0, and now the boundary conditions on the left end of the specimen is done. The right side we have same thing to do. Let's name it displacement, and here we can click on it because there is only on one edge, and we can say x can be anything and all the other degree of freedoms has to be 0. Okay. Now at last we have to introduce the load. The load is a concentrated force which goes on the release point 1. Can create a set if I want to. Let's call it release point. And I can say here 7 kilonewtons and 0 newtons in all other directions than x. Now that the load is defined, we just have to define the crack. The crack is defined in the interaction module with special crack create. And there we use debonding using VCCT with the initiation step 1 and the contact pair initial 1. We just only have one contact pair. And the debonding force could be anything because we don't see debonding happening, but usually you have step as a debonding force. Now we're good to go and define a job. I'll pause it here and we'll come back until when the simulation has finished. So the job completed, but there was a problem with it, as I did forget to include the bonded node set in the contact definition after we created it. So the bonded node set have to be specified in the contact definition as the bonded node set. With this step done, we will restart the analysis, and I'll come back to you soon. Now the simulation is done and we can check the results. First, let's see the deformation plot, which seems valid. You can see on the right side that the rotational degree of freedom around the y-axis has been constrained properly. And the bending moment does its work, as you can see here. Let's reduce the scaling factor to 10 and check the strain energy release rates. We can look them here, energy release rate 1, and you can see the values are only at the crack tip. We can plot them in different ways. The first way is we can define a user-defined surface plot. We can do that with tools. Display, let's see. Tools create field output from fields. And here we can, for example, show G total by adding G1, G2, and G3. G1 plus G2 plus G3. Okay. Now what Abaqus does, it creates a session step. And there we have our values. This is G total over the width of the specimen, and we can probe the values by clicking on it, nodes. Now the maximum values are 0.33221. Another way of looking at it is to define a path. Let's see if my paths work here. One is working. We can plot, for example, the strain energy release rate 1 over the width of the specimen and each time we hit plot, Abaqus will create a temporary container here which we can edit, and the values are listed in here and can be selected and transferred to Excel or any other software you want to use them. This concludes this tutorial. Thanks for watching.